Here is another problem that I'm also really excited about. Calculate the volume of a sphere. Okay? So again, this is one of those equations that you know from many years ago, but probably nobody has ever proven to you, right? So if we go to Wikipedia, we all know that the volume of a sphere is just 4/3 of pi r cubed. However, if you read Wikipedia, actually this is very interesting. Archimedes first derived this formula. Okay, so imagine, Archimedes, if you go to Archimedes' webpage, so he was born in 287 BC. So they already had Euclid, so they already had the Pythagorean theorem. So there was a lot of many things that were known in the time of Archimedes, but nobody knew the volume of a sphere. Can you imagine that? Can you imagine being Archimedes? He was fascinated with geometry, and nobody knew the volume of a sphere. How great must he have felt of finding the volume of a sphere? So it says here that Archimedes anticipated modern calculus by applying concepts of infinitesimals and the method of exhaustion to derive and rigorously prove a range of geometrical theorems, including the area of a circle, the surface area and volume of a sphere, the area of an ellipse, and the area under a parabola, the volume of a segment of a paraboloid of revolution, and so on and so forth. So lots of areas and volumes. He was the first one to derive them. So now you know how to calculate the volume of a sphere. However, what about the surface area of a sphere? I still haven't taught you how to calculate the surface area of a sphere. And you won't know how to do that until I teach you about surface integrals, which is next chapters, okay? But for now, let's go back and calculate the volume of a sphere. I can guarantee that if Archimedes had known about this problem that I'm going to solve in like 3 or 4 lines, he would have loved it. I don't know, maybe he would have been disappointed because maybe he spent years trying to find the volume of a sphere, and now we are going to do it in less than 5 minutes. But let's go ahead and do it. So the volume of any object is the triple integral of dv. Okay? And this triple integral is done within that volume v. So we are going to use spherical coordinates. So spherical coordinates are great because then the volume of the volume determined by the sphere is simply changing r between 0 and capital R. It's changing theta between 0 and pi. Remember that theta is the angle with respect to the z-axis, and it goes from 0 to pi. And changing phi between 0 and 2 pi. Remember that phi is the angle around the z-axis. Okay, so those are the limits of integration. While dv, we derived it just now, or you can look it up in a table. For spherical coordinates is r squared sine theta dr d phi d theta. Okay, so let's calculate this volume of the sphere. I was just thinking, Archimedes didn't even have Arabic numerals. So he was doing sticks for numbers, 3, Eve for 4, and so on. Can you imagine calculating the volume of a sphere? Okay. So let's do it. So we are going to do the integral of this dv, which is r squared sine theta dr d theta d phi. So what are the limits for r? They are from 0 to capital R. What are the limits for theta? From 0 to pi. And what are the limits for phi? They go from 0 to 2 pi. Okay, so this is the triple integral that we want to do, because this is dv, the differential element of volume in spherical coordinates. So now the good thing is that our integrand can be written as a product of a function of r times a function of theta times a function of phi, which we could take as 1. So therefore we can do separation of integrals. 0 to 2 pi of d phi times 0 to pi of the integral of sine theta d theta times 0 to r of the integral of r squared dr. Okay, so the first integral is 2 pi. The second integral is the minus cosine of pi evaluated, minus cosine of theta evaluated between 0 and pi. And the third integral is 1/3 r cubed evaluated between 0 and r. So this is equal to 2 pi times, what is the cosine of pi? It's -1. So minus 1 is 1. Minus the minus cosine of 0. So the cosine of 0 is 1. So -1. So this is 1 plus 1. And here we have 1/3 of capital R cubed. So now we have 2 pi times 2 times 1/3, that is 4/3 pi r cubed. The volume of a sphere in literally 5 lines. Great, fantastic. So thanks for watching and see you in the next video.